Greetings! This is Group 12 from Section EG2 for the course Differential Equations. I am Exai Nicole Viernesto, and along with my groupmates, we will be discussing differential equations in beam deflection. We learned from our earlier calculus courses about derivatives and integrals. To recall, derivatives are used to indicate rates of change in mathematics. But what do derivatives have to do with differential equations? Differential equations are equations that link an unknown function to one or more of its derivatives and are frequently used in mathematical models. Relationships between changing quantities are the core of many physical problems, thus the importance of differential equation. As aspiring engineers, we want to be able to perform complex calculations which will enable the translation of the vision for structural projects and developments into functional, cost-effective, and buildable structures. Buildings and bridges are made up of a variety of components, such as beams, columns, and foundations, all of which work together to guarantee that the loads carried by the structure are securely transferred to the supporting ground below. A beam is a structural element that can bend and endure enormous loads. Horizontal beams are typically built of steel, wood, or reinforced concrete and have a cross-sectional shape that is rectangular, T or I. The design of these beams can be complicated, but its purpose is to ensure that the beam can safely hold the load it was designed to support. Rigidity, rather than strength, is typically used to build beams. Moreover, additional aspects must be taken into account when designing beams, such as determining the beam's expected deflection under load. Because the force of gravity will cause some bending, the beams themselves will not be horizontal over time. They experience small form modifications. As a result, we assume tiny rotational angles and very minor deflections. Excessive deflection of beams can cause visual discomfort to building users, as well as damage to sections of the structure and build partition barriers between rooms and utilities, like water and heating pipes and ductwork. Hence, it is important to calculate the actual beam deflection under the expected design load using numerical methods and compare this number with the permitted value to determine whether the chosen beam section is sufficient. As a component of these calculations, we must determine the maximum deflection that will occur in the beams of the structure and guarantee that they are not excessive. Beams are one of two structural elements that are integral to the construction of a safe and sturdy foundation for a structure, which is especially important in the development of large-scale buildings. Determining the deflections of beams can be done using a variety of analytical methods. The differential equation that relates the deflection of the bending moment is a common one.
The deflections of beams are computed using the fundamental formula based on the beam curvature. Curvature is equals to 1 over r equals m over e times I equals the second derivative of v with respect to x. R is the radius of the shape of the curved beam at the distance x from the origin, normally taken at the left or right-hand end of the beam. E is the elastic or Young's modulus of the material. I is the moment of inertia of the beam's cross-section. M is the bending moment at the section distance x from the origin. V is the vertical deflection at the section distance x from the origin. In this formula, E and I are generally constant numbers, whereas V, x, and m are variables. M can be expressed in terms of distance x. Hence, the deflection V can be computed by integrating the expression twice. When the elastic line or the deflection curve AB is observed, one can see that the curvature at each point varies, making the slope vary at different points as well. Two axes, x and y, are taken to describe the deflected shape of the beam in rectangular coordinates. The x-axis corresponds to the beam's initial straight axis, while the y-axis depicts the deflection. At the ends of this element, the normal, which intersect at point O, is created, indicating that the angle between these two normal is equal to di. However, for the deflected shape of the beam, the slope I at any point C is defined as tan I equals derivative of V with respect to x, or I equals derivative of V with respect to x, assuming tan I equals I. Considering an element ds of the deflected beam, we get ds equals r times di. However, ds equals dx, usually for small curvatures. Hence, ds equals dx equals r times di. Substituting the value of I, we get second derivative of v with respect to x equals 1 over r. Substituting this to the simple bending theory equation, m equals e times I over r, we get the differential equation governing the deflection of beams, or the deflection curve v. M over e times I equals second derivative of v with respect to x. One method used for determining the deflection of the beam is the direct integration method. That is, the approach using the differential equation we have derived earlier. Indefinite integrals produce integration constants that can be calculated using the problem's boundary conditions. By integrating the curvature equation once, we can get the slope of the beam. And by integrating the curvature equation twice, we can get the deflection of the beam.
The next section will be the discussion of an example problem. This integration process will be illustrated using the example cantilever shown in the slide. For this beam, x equals 0 is located at the free end of the cantilever on the left, and therefore x equals L at the fixed end on the right. The entirety of the beam is made out of a single material and has a constant cross-section. So therefore, E and I are constant, meaning that neither of them is a function of x. The first step to solving this problem is finding an expression for the moment as a function of x. So it is possible for us to integrate this, so that afterwards the curvature can be found, given that EI is constant. The expression is then integrated once for the slope and twice for its deflection. C and D, as seen in these equations, are both constants of integration, and this can be eliminated using known information, and these include information about the displacement or rotation boundary conditions. For this specific problem, we know that there is no vertical displacement or rotation at the fixed end where x is equal to L. And because we know that there is no vertical displacement or rotation at the fixed end where x is equal to L, theta L is equal to 0 as well as delta L. These are then substituted into both the slope and deflection equations as seen below in order to solve for C and D. Then after we solve for the constants of integration, these are then substituted back to the original equations to give us the following answers. And lastly, to conclude this final project, engineers must be able to represent physical problems using mathematical equations and then solve these equations in order to investigate the behavior of the systems in question. The complex processes involved in differential equations can provide us with different practical applications as much as it does in theory, just like in beam deflections. Thank you for listening, and the next slide will be the references we used in the project.